We go here. Hi everyone, I'm Robert. We'll be doing chapter 11 this week of the book. Just a few words about myself. Started out as a physicist a while back and worked in defense for a while on some problems involving target recognition from aircraft and landmine detection. And more in the field, just realized that machine learning was the thing that I needed to learn, and that my physics training had only partially prepared me for that. So the last really 6, 7 years, that's what I've been focused on is just developing that expertise in machine learning. Been studying it in a variety of venues, and right now I'm a machine learning engineer in government consulting, and also teach at the local university here in Northern Virginia, George Mason University, where I also completed a data engineering degree recently too. So let's jump right into chapter 11, and this this for this meetup here, we've been discussing various chapters of this book. And I'd like to emphasize the discuss part of that. I don't envision this being a an afternoon where I just you know tell you everything that's in chapter 11 of the book. For one thing, there's not enough time to do that in the hour. And for another thing, I really want this to be a conversation. Whatever you're interested in, please ask. If the conversation gets too off track, I trust that Ted and or Ryan will help us rein it in. Would be nice to cover most of the ideas in chapter 11. I have created some slides and have posted to the Slack group that are an outline and could serve as a point for our discussion, but I have no need to speak through all of them. Let's take this conversation wherever interested in. That being said, chapter 11 is there's a lot of different techniques presented here. And it's a huge leap, I think, beyond where we were last week, where I think we were focused on a lot of real basics of neural networks. And Jerry laid a really great foundation for us last week in the slides that he put together. So this time it's getting down into the weeds a little bit as far as the training process. So please feel free to ask questions and participate so that you can get out of this discussion what you would like to. Let me share my screen, and I'll just share the whole desktop because I'll be back and forth between the slides and the collab notebook that Aurélien Géron published with this book. Can you see the slides on my desktop now?
Yeah. We're good. Sorry.
Awesome. So there are 4 basic sections here. We're going to be talking about the vanishing and exploding gradients problem, which can make it difficult to train your neural networks. We're going to talk about reusing pre-trained layers, which is one method for speeding up training. We're going to talk about how to improve your optimizers. And we're going to talk about regularization that can help you avoid overfitting and improve generalization in your neural nets. So last week we saw how to put the basics of dense layers into practice. This week we'll be exploring some of these command line options and arguments that you can pass to a layer or to an optimizer or a loss function, etc. And I think I wanted to step back and provide a little bit of perspective, and one quote that I've always found helpful in my own machine learning journey has been the Goodfellow book here by Deep Learning. Great tome on the subject. A little bit older now. So, but this recipe for the ingredients that go into an ML model, very oversimplification, but it's useful to think of that an ML model consists of a data set, a model architecture, so the data set here, the model architecture, a cost function, which we're going to call a loss function in the deep learning world, and a procedure for optimization. And it's through combinations of choices in all of these four ingredients that really lead to the diversity of models that you can create in deep learning. So we're going to start by talking about some challenges for training your neural net. And one of those challenges is the issue of vanishing and exploding gradients. So what's going on here? In the networks that we saw last week, we had pretty shallow networks with not a whole lot of layers. And in those networks, you typically don't have to worry too much about how your gradients are propagating from one layer to the next. However, in today's much deeper neural networks, such as this sample, I think this is from ResNet 101 block over here, there are many layers that may be chained together. And if you have many layers chained together, you can have an issue where it's very difficult to propagate the gradient through all of those layers unless those gradients are extremely well behaved. For example, if the gradients on average have values that are less than 1, then they will multiply together in all of these layers, and you'll get extremely small gradients when you're trying to train the lowest layers in the network. On the flip side, if your gradients have higher values, you can get exploding gradients and some unstable behavior. Vanishing gradients is the more common problem, and it was really elucidated first, I think, in this paper by Xavier Glorot and Yoshua Bengio in 2010. And this was the paper, I believe, that introduced the Glorot initialization procedure. But they illustrated why vanishing gradients should be expected, actually, in the early neural networks. And if you think about it, the sigmoid activation, if you plot this function right here, and you look at its behavior, the derivative in the middle of this function is less than 1 already. So your derivatives go to 0 at the ends, very small. And even in the linear portion here, you still have a derivative that over hundreds of layers will end up multiplying down to 0. And this visual down here in the lower right is one illustration from that original paper showing how some of the lower layers really struggled to learn, how they were pegged to either these really low activation values or these really high activation values. And you can see here that in this one, layer 1 has lots of values that are just going up here to high values, and that over various epochs, as the training procedure just continues on, the values get more and more pushed to the extremes, which makes it more difficult to learn. So one approach for addressing this is to be smarter, more clever about how you initialize your neural net. And a number of approaches have been taken for that, and this Glorot approach is one of them. And the observation in this paper was basically that you want the variance of your input and output activations in a given layer to be roughly equal, so that it doesn't increase as you propagate forward through the network. Likewise, you want equal variance of input and output gradients so that you can backpropagate through the network without growing or decreasing. So the Géron book here describes the Glorot initialization as well as some other ones. The Glorot one was specifically designed back when softmax and logistics were the most common activation functions. Since then, we've had some activations. ReLU has become much more popular, and with the ReLU, you get a different initialization published by Hey, with a very similar but slightly different magnitude for the recommended initialization of the layers. There's also a thing called a scaled exponential linear unit, which Jan LeCun first published probably 20 years ago. And that has the interesting property that if you have a sequential network, you can actually have what's called a self-normalizing layer. So you don't have to worry too much about how you initialize. It's roughly going to stay the same throughout the training process. And this is described in detail in the text, each of these initializers.
Question. So there's several different, 3 different initializers, and they're all they all have a variance of 1 divided by fan and 2 divided by fan and 1 divided by fan in IN. Hello?
Yes. Was that a question? I didn't hear a question. I'm sorry.
Oh, sorry. So the 3 different initializations, they all have are based on a normal distribution of or a uniform distribution, right? Just to kind of confirm.
Yes, you'll get a slightly different recommendation if you're using a normal versus a uniform distribution. The idea is really to put them on the correct scale.
Oh, okay.
And that scale is determined by the number of neurons in the layer coming in and the number of neurons in the layer coming out. And that's what's really meant by the fan in and the fan out.
Okay.
And the fan average, I think, is that's the one that Glorot was writing about. But it's identical. If fan out equals fan in, like if your layers are the same size from one layer to the next, then the LeCun version is going to equal the Glorot.
Oh, I see. So it scales depending on how many layers you have then.
Hey, Robert, I was thinking, like at the end of the day, inside of our neuron, right? What we're doing is we're just multiplying weights by multiplying each input by a weight, and then we're summing them all up. So you can just imagine intuitively, if you have a unit that for some reason only has 2 inputs, and you multiply them by your weights, well, then you're going to get whatever scale the inputs coming in are. Let's say they're on the scale of 0 to 1, right? You're going to basically, double that because you've got 2 inputs coming in. But if you had a neuron that had 1,000 inputs, then if you use similar size weights, right, just because it's got 1,000 coming in and we're adding them all up, you're going to get a much bigger output. And so that's why this thing is saying that you divide by fan in, because the more inputs you have, you just need smaller weights in order to not have the output be a lot bigger than what the inputs to that neuron was. So I don't know if that helps with intuition.
Yeah, that is a nice way of thinking about it.
I've tried fancier functions for activations, just in particular the ones which use exponential function like Ceru does, and they usually slow down calculations. Anything?
Well, there's two different measures of speed. So one measure of speed is how long does it take your computer to calculate a forward and backward pass on your data, right? The other measure of speed is how many iterations, how many epochs did it take for your neural network to converge? And so with the fancier activation functions, what they're usually saying is the second thing, that it's faster to converge, not necessarily that it's faster to compute each actual pass.
Oh, okay, thanks.
If you look at the activation functions themselves and you think about it, it's pretty clear that ReLU is really fast to compute relative to these other ones, because it's just you either turn it to 0 if it's negative or you spit back the same number. There's really no computation that has to be done. So that can give it certain advantages. But if the other ones converge in fewer epochs, then that's the trade-off. So that's a nice transition into the next section in the book. Each of these slides, by the way, I think I tried to just put one slide with a few visuals for each little subsection in the chapter. Non-saturating activation functions was the next one, and ReLU was the first one described. And it's a bit interesting historically that the reason, at least the presumed reason, that the sigmoid activation and logistic shaped activations in general were so popular in the early days of neural networks is that there was the analogy with biological networks and just an assumption that, oh, if biology is doing it this way, then that's the most efficient way that we should be doing it for artificial neural networks as well. Now, one difference is, of course, if you think about it, biologically we have to generate signals in an analog fashion. So our systems are probably not capable of mimicking a function like ReLU. There's a reason that the signals are limited. However, for computation artificial neural networks, it turns out that the ReLU function and the fact that it does not saturate is really useful, because it solves the vanishing gradient problem. You will not have a vanishing gradient if you're up here, because it's increasing constantly no matter what the value is. You can have a vanishing gradient if you're down here, and suppose all the data samples for a particular neuron put you down here in the negative branch, then all of a sudden you get what's called a dead neuron, because further training cannot move it unless previous layers for some reason are then readjusting the values coming into it. But that is an issue and can sometimes reduce the size of your network that you were intending to put in. And because of that, people reasoned, okay, maybe we need a slightly variation on the ReLU, and the leaky ReLU was born out of that, where the idea now is we still need to have some kind of a knee in the curve here in order to break linearity, but what if we have one that down here is just not quite as, this is not 0, so that at least we can still learn something down here, albeit maybe a little slower than we would learn it if it were up here.
So anything, I guess, past 0 and lower, it's going to lead to a neuron that doesn't really propagate to the next one, right?
For the ReLU function.
Or just the ReLU, okay.
Not you have to think about the fact that if you're feeding in a data set with many, many thousands of examples, any given neuron is likely to be activated, where I'm calling activated in the positive side here, it's on. And so chances are that every neuron will be activated by some samples, and then every neuron will be readjusted upon the end of an epoch. It's only when all the samples end up over here that you get a dead neuron.
I see. I see. So at least like one, at least a few of them are in the are greater than 0, then you'll still be okay. But if they're all dead, then if they're all on the left, then yeah, it's a done deal. Okay.
These two further activation functions at the bottom, the exponential linear unit and the scaled exponential linear unit, are an attempt to address the ugliness of this little curve right here. Exponential linear unit is actually differentiable throughout. The slope is matched right here. And the scaled ELU is not. It's the one that Jan LeCun came up with, and it's an interesting. If I pop out of here and go back into the notebook, we can see how it's defined. It's a let's see. It's a very long, complicated function of pi and e and error functions and the like. This looks extremely complicated, but it's not really a function of anything. It's just a big constant. And what LeCun observed is that using that big constant and multiplying just the negative branch by that constant, you could, in fact, produce what he called a self-normalizing network, which prevents the gradients from growing or shrinking during the training process. Because it only works for sequential networks, it's not, there are many other approaches in use now, but this is one interesting one to keep in mind.
Is there a name for that constant?
I'm not aware of a name. Has anyone heard of? It certainly doesn't look like something that would have a name. Otherwise, if it had a name, there would be a shorter expression for calculating it.
Honestly, I don't think I've seen Selu used in anything
Yeah.
that's remotely recent.
ERFC, that's error function, right? I believe in
Yes.
math. Oh, I see. Oh God. Okay.
One comment I might make is that when it comes to initialization and activation functions for your main backbone architecture, I don't know that it's that important to know, because unless you're going to be a researcher, I don't think it comes up that often. You're generally following the footsteps of other people who've spent a lot of time experimenting and figuring out, good combinations of all this. But if you want to just understand some of, the basics of how, what's in, the BERT architecture, what's in the VGG architecture, what's in T5, you're going to hear these terms. And so it's probably very useful to at least have like a high level understanding of the different activation functions and things like that. The one place where you do need to understand is on your output layer. Something like a sigmoid will constrain things between 0 and 1. And so if you're doing, say, binary classification, that's when, you're going to use it. If you're doing multi-way classification, you do the similar multi-way softmax. So that's like the one place where you got to use it. But even then, I don't know, no activation, softmax, that's pretty much all I use. I just thought I'd throw that out, Robert, just in terms of like,
Yeah, I think that does put into perspective that for the vast majority of practitioners don't really need to understand the differences between these activation functions. So it's very academic and it's in the weeds.
So in some sense, it helps to know, but probably don't want to waste too much time on that, right? I guess is that a message? Okay.
Yeah, I don't think you need to know it inside and out.
Okay.
And it's something that you can learn after getting experience just keeping simple activation functions, and then maybe once you have a specific problem where it makes sense to explore these new ones, you can learn them.
I see.
It's in my experience, there are certain people who like that's their entire research subject is just looking at activation functions and normalization schemes and stuff like that. And it's extremely useful because it's so general. It's in every single network. So if you can get a 1% gain across every network that's ever trained in the world, that's an amazing accomplishment. But in reality, it also is the case where it's like, okay, well, maybe you switched from sigmoid to whatever the newest, most state-of-the-art thing is, and it's a less than 1% difference, and you don't really care that much. So it's something that's important, but maybe not specific to your scenario that it's like that crucial.
Mm-hmm.
I got a, well, not really a question, but like more of a, well, kind of a question, yeah. Is it because of the symmetry of normal distribution and the uniform distribution that it doesn't either lead to vanishing or exploding gradients? I just had a hunch.
It's kind of difficult to answer that question because there's a whole bunch of things going on in the neural network. A lot of people have done research on that, and looking at batch normalization that we'll just talk about, there's people that have some explanation of what batch normalization is doing, and it's not entirely clear that we're totally confident on that either. So there's a lot of different parts that are all interrelated, and we don't have complete explanation of all of the phenomena.
Fair enough. Fair enough.
Yeah, batch normalization is a fascinating phenomenon, and having one slide on it and a couple minutes to discuss it is not close to doing it justice.
Right, my bad. Sorry.
It's an interesting tactic to try to prevent gradients from growing during training. It's like you renormalize the activations at each neuron to make sure that they stay within a certain range. You enforce that during training, and you do that by calculating these batch statistics. And then the question is, why does it work? There's a couple of interesting resources that start to think about that question here. First of all, there's a pointing to the original paper by Yoff and Szigeti. There's a blog post here that I think is very helpful. At least I found it helpful when I was first trying to figure out what batch normalization is. Why might anybody do it? And there's also a Colab notebook down here by David Page, which is linked to from this blog post, which does a pretty deep dive into distributions of activations before and after batch normalization. The algorithm itself here, it's pretty simple, but as Ryan was saying, there's a lot of debate about why does it really work? Is it because it's forcing your network to be resilient to changes in the distribution, internal covariate shift? Is it because it's smoothing the gradients and making your training a little easier? Is it because it's regularizing? Is regularization just a side perk to doing it? I'm not aware of any real consensus within the community as to this is exactly how batch normalization works and why.
That's cool. Understood.
Are there any parameters around the gradient problems for when you would want to apply this? In other words, what would trigger one's intention to use batch normalization?
So the only thing I can think of is that for certain for deeper networks, the deeper your network is, the more likely you are to have gradient problems. So in that case, the more likely batch normalization is to be useful. Batch normalization is implemented a little bit differently if you have a convolutional neural network, as is described in the book, layer by layer instead of neuron by neuron. Not sure what impact that has. But in general, it's so ubiquitously done these days that a lot of times people don't even bother to mention it. It doesn't seem to. I'm not aware of cases where batch normalization really hurts. So it just seems like it's something that's pretty standard now.
There's no reason not to do it, in other words.
Any other thoughts on that?
If I can chime in, so one of the things that you just said was it's done kind of layer by layer, right?
Mhm.
So one thing that's noticed with batch normalization is we don't, so you know how there's like one type of equal sampling, so your model gets like equal parts of data. Batch norm layer by layer also sort of has an impact where it makes it so that each layer has an even distribution of features. That's one of the benefits that's been brought up, so that like we don't have one layer that just looks at one feature and it has its own gradient issue. So there's been some research to show that it helps there. And additionally, one of the reasons that we don't talk about it too much anymore, or we start to like see the lack of benefits, is because it's still complicated to in terms of compute. So there's not much like benefit to doing it if you don't see the benefit. So sometimes it's skipped out. Like there are a lot of memory issues with new models like transformers and stuff. So adding batch normalization layers, sometimes it just adds compute because you technically have to do stuff in batches. So sometimes you'll see people just use a batch size of 1 even, but you're technically forcing more compute for places where we sometimes just don't see benefits. So it's not like you always just do it because you can and it's like not harmful. It does technically add some compute. So that's why some like newer papers I've been reading have been leaving it out in a sense. But yeah, just some stuff I've picked up on it.
Yeah, and you just kind of alluded to a point I was going to make here, where there is some research now where people are finding that maybe it's not really necessary under certain circumstances. You're getting just as good a results without it. Um, so yeah, there's definitely a discussion to be had there.
I just would like to mention something very generate. Why we do normalization again at all? The thing is that if your numbers became very, very small, then you push them pretty much into the area where truncation errors could become rather significant. And so if you can increase your numbers to the kind of medium range between, well, usually they get between -3 and 3, that it will give you more, but it will give you better calculations.
Mm-hmm.
Yeah, there's definitely that benefit of
accurate.
numerical stability.
Yeah, one
I would
thing
say
I like about it is the aspect of regularization, right? What it basically does is for a given training sample, there's a distribution of activations that it could produce. So like instead of feeding the exact same data in every time, you're getting for each sample kind of a fuzzy set of values for that sample. So it forces your network not to draw very strong lines between samples because it has to be able to react to a variety of values for any given sample.
Yeah, that's an interesting thought. So I just wanted to reinforce. So based on what Vibhu said, the main downside is just computational cost, memory and compute. And then you will see, without going into all the gory details, that there are other kinds of normalization people do. So if you look at very recent architectures, you'll see other things that have normalization in the name of the layer. So layer normalization, channel normalization, but the concept is similar, where basically they're trying to make sure that that your outputs are in, as Maya said, in sort of a nice centered range, and that they're not getting too big or too small either way.
Yeah.
Just
The other thing,
reiterate, the one thing, Ted, I'm not sure if the only con is computation and cost. That's just one of the main ones that I've read a lot about. I haven't really looked into it too much. I'm sure there may be other reasons not to use it. I was just kind of sharing a point of some research of some recent articles I've read, but there could be other ones other than just computation. But that's what I've seen focused on. I read a couple papers that were like newer vision transformer models and whatnot. They're not using it because it's not showing benefit, but it's adding compute resources. It's kind of taking away from that. So there's a chance that was just specified to those kind of papers, but yeah, there might be other cons to using it as well. Not too sure.
Yeah.
The
Go ahead.
the other thing is, in things like transformers and a lot of these new networks, now they're bypassing, they're essentially wiring this layer to another layer, 40 layers down or something, just as a skip connection. So in terms of having to propagate data all the way through, they're just sort of back running it, almost like, you just said, ship all this stuff off to this other layer, and who cares if it goes through the intermediate layers?
And for people that are interested into why it works, that the paper I was reading, it got technical into like something about convergence based on certain eigenvalues and like mathematical theory, which I can't remember off the top of my head, but I'll link it in the Slack at some point. But they got like a technical reason for why batch norm works as a type of regularization, and for their use case, why it was not applicable, but it was more than I cared to learn at the time.
Cool. So we're definitely progressing through the chapter slowly, which is fine, but we'll need to figure out what we want to do. I think we're about halfway through and have covered about a quarter of the material. Gradient clipping is just another thing introduced at the end of the vanishing gradients thing. Not especially difficult. Just one way to stop gradients from exploding is just simply clipping them. I think let's move on to section 2 on pre-trained layers. So one really useful thing that so many people are doing these days is what's called transfer learning, where you're essentially leveraging someone else's trained network to solve your problem. Because so many of the things that a neural network learns are low-level tasks that might be useful for a variety of outputs. So in the visualization here from the book on the right, we see that you have some task A, network trained for task A, and you might freeze a couple of the lower layers and say, well, these ones here that are just detecting edges and lines, maybe that's useful for my vision task no matter what the output task is. And then further up the network, I need to be a little bit more specific. So let's ponder a case where maybe we have a computer vision model that's trained on ImageNet to do classification amongst the ImageNet classes, but now we want to classify, say, between all these different kinds of cars. And ImageNet may have a couple different sorts of vehicles in it, but it's not these ones. However, the model that we've been using has already learned in the lower layers how to do edge detection. Maybe it's figured out how to detect a wheel or a window, but it's also trained on dogs and people and objects and other things that aren't really related to cars. So it's got a lot of other things that maybe we're not using, especially in these upper layers. So what we'll need to do in the new model that we're going to do for task B, we're going to have to replace the output layers. Maybe we have these 20 classes here, so we're definitely going to need a new output layer. And then we'll want to retrain these, or I'm sorry, we're going to want to train these upper layers, and we may want to retrain a couple of the upper layers that we're borrowing from the original model as well. So this can save a lot of time and effort over trying to train this new thing from scratch, because it could be that 90% of what the old model has learned is useful for us, and we can save a lot of time that way. So the example that is presented in both the text and the Jupyter notebook, a Colab notebook, is an example from Fashionist. where, okay, suppose we have trained on not Fashion MNIST itself proper, but we've taken 8 classes from Fashion MNIST, all these ones except for the 2 that are outlined here, and we have a model that's trained to recognize those. Can we use that model to produce a binary classifier, or to transfer that model to a binary classifier that can recognize the sandal versus shirt case? Even though the original model hasn't seen sandals or shirts, the concepts and visual aspects that it has learned in recognizing these 8 classes here are very useful for telling the difference between sandals and shirts as well. So there's a little bit of code in the notebook, and basically shows how simple it is. You're really just loading a model. You may change the upper layer and then retrain it. And there's some advice given on how to train it in the text, where you might start by freezing the middle layers. So you're going to keep the lower layers frozen at all times. But you might as well start by just training the very highest layers. And then eventually you can turn on the middle layers for retraining. The reason you might want to do that is that if you take all the layers you intend to retrain and start training them immediately, you may run into some pretty big gradients at first because of the untrained layers you threw on the top, causing things to go out of sync. And then it may mess up a lot of what your middle layers have learned. So if you kind of gradually train the upper layers with the middle ones frozen, then you can come back and tweak them to better do your own task. And oh, go ahead.
So the order of which layers you choose to train with matters in this sense. Just to avoid possible gradient, vanishing or explosion, I guess.
Yeah, there are recommendations. You can imagine that if you start with the network that you're transferring from, and all of a sudden put a randomly initialized output layer on the top of it, then for the first few epochs, it's going to do really terribly on the sandals shirt classification. And if you haven't frozen those middle layer weights, it might want to change those a lot, whereas it could have done reasonably well with those original weights if you just let it train the new layer first on its own.
I see. Cool.
Now, the example that Géron provides in the book is kind of funny because what he likens it to makes the analogy with the model is confessing under torture. And what he actually did was very much searched for a case where transfer learning appeared to be providing great results, where actually it was more of a statistical fluke. And what he said was that transfer learning really doesn't work very well with the case that he provided, which is very small network, dense layers. Transfer learning is going to provide the biggest value when you've got large networks with a lot of lower layers that you've learned previously. These shallow, dense networks often learn a lot of very specific task-related things at all layers, which don't necessarily generalize very well to new tasks anyway. So transfer learning may be less effective in those cases. But the lesson of really trying to figure out, is the effect real, or did I force my model to confess under torture, is a useful thing to keep in the back of one's mind whenever building models in machine learning.
So Robert, if I could just reinforce, transfer learning is probably one of the most common ways that people are likely to use deep learning. So rather than building a network from scratch, you're going to take a pre-trained thing for image classification, a pre-trained language model, a pre-trained, you know, something, and you're going to reuse, you know, 90% of it, and you're just basically adding a little bit on top and doing retraining. And then this is where, again, knowing some of these things about it will help. Some of the stuff that we're going to talk about later in the chapter, like learning rate schedules, those are things that you actually may play with. The earlier stuff on the architectures and the you know, normalization layers, whatever, if you're using a pre-trained network, that architecture is already baked in.
Yeah, and this just builds on human experience as well, right? From infancy, we learn how to classify things, and we learn how to look for edges and shapes, and we learn that if you have a certain thing, it you know, with wheels and windows and all, it's a car. And this is really just extending that concept to ML, where you don't have to learn everything from scratch. You can use your life experience or someone else's life experiences to learn from. It's kind of the artificial analog to that. So
I just want to mention, I mentioned it already last time, I work with the data, with this ministration data, and I discovered that it is not classified well. That there, in particular with shorts and t-shirts, there are a lot of women tops which do not look much like short to t-shirt. So I wonder if the author would get a better result if he would work with something which is definitely classified well, like say trousers and bugs.
Yeah, and I mean, there's been lots of people who pointed out problems with ImageNet, even though so much that we've learned is based on, you know, ImageNet models, that ImageNet has some weird labels in it.
I think part of MNIST's problem is you only have 28 by 28 images. So there's, you know, I think if you had a higher resolution image, it might do quite a bit better.
Yeah, it's good for learning. It's good for playing around with something that's not going to take forever to run.
Yeah, I think that's a point. You can go in and tweak it, you know, in moments and rerun it and see the impact versus having to train it for an hour or something like, you know, some of these other image recognition networks.
but one reason for the existence of fashion MNIST is that performance on MNIST over the years has gotten so good that it became less useful as an image classification benchmark dataset. So this takes the place of that, you know, really small images, very simple to learn with, very simple to experiment with, but still is a challenging enough task that you know, not everybody's getting perfect performance.
So can I ask, is confession under torture, is that a bad thing? Or would we say that because it can't be applied on a larger scale generally, like if we increased the, I don't know, the types of images, it can't be applied, so then it's bad, or is it okay?
So I didn't really elaborate on what the author meant by this analogy, but he gave the impression that he tried a lot of different settings regarding the learning rate, regarding the random seed, other aspects of the training process, and selected an example that highlighted really strong performance, like the transfer learning just did really well versus not using transfer learning. And what I think one point that he was trying to make is that a lot of research publications follow the same pattern, right? Where you're looking for something impressive, and then when you finally see something impressive, you rush to publish it. And if you don't really stop to think about, well, how much duress did I put my model under? You know, was I doing the equivalent of putting the model in the interrogation room and asking them 200 questions without giving them a break for water before they finally confessed?
It's
Yeah, I
kind
mean,
of like, sorry, it's kind of like cherry picking what you report.
That is the word, yeah.
Yeah. So the whole concept of having a test set, right, is that you validate the performance of your model once and only once. But ultimately that can break down if you build a bunch of stuff and then you say run it against an ImageNet test set and you're like, oh, the performance wasn't as good as on the training data. Let me go back and do more research. And you try some different things and you're like, okay, I've tried 100 different models and this one's the best. Let me try it on the test set. Oh, wasn't that great? You do that 100 times and then you may just by fluke get something that performs well in the test set, but it doesn't mean that that model is actually any better than the previous 99.
It basically means at that point you've used the test set as a validation set.
Right, even though you technically didn't, right? I mean, you each of those times you built 100 different models and you validated them without looking at the test set. But then at that point you peaked, and you didn't publish it. You peaked, and then you said, "Oh crap, this wasn't as good on the test set." So then so yes, so that's where exactly what Roger's saying is that you had good intentions, but you basically are now overfitting to that validation set because you peaked 100 times.
Mm-hmm.
That goes back to, Scott Page's whole kind of rather profound point about any really good analysis is based on multiple models. Like you should have at least, if you've got a training set and you can produce at least 2 or 3 different ways to model it, then you're going to be better off than just sticking with one, even if you get a really nice fit for the data.
I think I saw something, it was like a interview question, prep kind of a thing or whatever. And it was like a true false kind of a thing where it's like, oh, you train this, whatever. And number 4 was the one that had the highest score. So you should use model number 4. And it's like, well, no, you might have just gotten lucky, right?
Yeah, to some extent, first principles should come into play as well, right? Like how likely should you have expected before that model 4 would do well? Another thing that the author emphasizes in this section on reusing pre-trained models is unsupervised pre-training. And one of the reasons for that is that a lot of times it's easy to come by data, but that the labels are what are expensive, right? There's so much imagery out there on the web, but how much of it is labeled to say, this is such and such car, or there's a lot of times there's captions. Sometimes those are automatically generated, sometimes they aren't. So there's one option that you could use is auto-encoding. And I don't want to go into this much now. This is a whole nother can of worms that we'll get into later in the book. But the idea is if you can learn interesting features from your data, such as in the case of face recognition, figuring out that what you need to do is detect the lines, the edges, and eventually detect the eyes, the nose, the mouth, figure out where they are, what shapes they are, how the face is reflecting light, etc. You can learn a small number of features. So the example that he gives here is a chess master. If you show a chessboard configuration to that person that is somewhat possible to see in a real chess game, the person can look at the chessboard in 5 seconds and memorize the entire board. On the flip side, if you show the same pieces but randomly put somewhere on the board in a way that would be very unlikely to ever occur in a chess game, the chess grandmaster will have no clue where the pieces were. And this is because the grandmaster has intuitively already developed latent representation space in his or her brain and has determined, this is how I visualize, this is how I interpret information. From my own personal experience as a musician, I can relate to, if I see pages full of chords and scales that I'm very familiar with, I can read it very fluently without having to spend much time looking at each character on the page because there's shapes that I'm familiar with. But if it's the same notes arranged in random orders or a random collection of notes, then I really have to basically read each character at a time. It's like a foreign language trying to interpret that. So I think it's the same basic idea. And if you can train your artificial neural networks in a similar fashion to represent concepts and features of your data in a latent space, that can be useful in an unsupervised fashion. And on a related note here, as far as pre-training, one of the primary examples of this unsupervised learning, of course, is that NLP, most language models today, are based on unsupervised pre-training. BERT is trained with masking, and you can reuse the representations of words and concepts for many other NLP tasks that the language models were not trained on. So that completes the pre-training section. Anything else we should discuss on that before looking at the optimizers? So one of the four ingredients that we discussed earlier is the optimization procedure. If you have a model, you give it data and a loss function, you still have this challenge of figuring out, well, how do I probe my space of parameters to find ones that will give good performance? This is a massive, complex optimization problem. Combinatorial optimization, generally, there's no way to solve the problem exactly. You just have to use heuristics and methods to guess where good solutions are. You will not be able to find a global optimum. Methods such as using momentum in the way that deep learning networks use momentum, or the way that optimizers may use momentum, have been around since almost 60 years at this point. The original concept was described in 1964 here. One thing I discovered at some point during putting this together was a pretty awesome distill pub on visualizing momentum, which I thought would be useful to interact with briefly here. See if I can find it around my Zoom window. This one. So you can imagine if you start with, let's start without momentum and see what the real problem is with optimization. So if we have no momentum and a step size of 0, well, we're kind of stuck at home. We're not going anywhere. Now let's increase the step size a little bit. All right. So what we're looking at is a number of epochs. I don't think it says exactly how many epochs there are for this problem. And let's look at the contour map of the space here. What we have are steep gradients in this direction and kind of a canyon down here. So we're going to go directly to the bottom of the canyon, and then we're going to try to move over here towards the optimum. But because our learning rate is so small, we're just not getting there. And so let's increase the learning rate, and you can still keep increasing it, but even up to 0.03, we're not getting there. And now we start to see another phenomenon. And over here on the left, we have the training process is moving us back and forth. So now we're kind of crossing the center of that ravine, almost like a ball rolling up and down this hill back and forth. And eventually, it's making a little bit of progress to the right each time. Eventually, it gets down here, and it's going to start moving more smoothly, but it's still taking many, many, many steps. And what happens if we increase the step size further? Eventually we get to a point where over here now we get steps that are growing even more than the first roll. They're actually increasing. And if we increase the learning rate even further, we're still not yet at the optimum, and we can get to a point where it gets very unstable. And at some point you may never reach the optimum, even over many, many steps. So how does momentum help us with this? So if we come back here to this, where we just first started to see some problems, or some oscillation back and forth, sorry, not a problem. What is momentum going to do? Momentum is going to look at past steps and try to do some kind of moving average on it. So that now instead of stepping back and forth, maybe we can learn some patterns from past steps and take steps that are a little bit further to the right in each group. So for instance here, instead of always going perpendicular to the contour lines, we've now realized, well, on the first step we went that way, on the second step we went back almost the opposite direction, but the vector sum of those two steps was actually in this direction here. So let's use that vector sum and then increase it a little bit by the gradient. And so you can see that when you're using momentum like this, each step that it's taking is much more in the direction that you actually want to go. And your solution is going to get much closer to the optimum quicker. And in fact, you can get to that optimum pretty quickly with the right combination of learning rate and momentum. If either one is too high, you're still going to break things, right? There, learning rate goes too high, you're going to have a problem. Momentum goes too high. At that point, you might be shooting way past the optimum and not really taking very useful steps. However, what is clear is that if you have the right combination of learning rate and momentum, you can get a lot closer to that optimum than you ever could without the momentum at all. Right? Learning rate down here, middle learning rate, and increase the momentum, you get pretty good numbers right in here without too much variation over the same number of epochs.
How would you define momentum here?
So momentum is actually a moving average of the recent steps that have been taken. And if we go back to the slides, I think there's a actual equation down here. Yeah. So,
intuitively, like if you were taking some steps northeast, some southeast, some northeast, some southeast, on average, you're going east, right? So momentum is just sort of saying averaging out, what the main direction is. Does that make sense?
Yes, thank you.
it's like an exponential smoothing of recent gradient steps.
I see.
So say you were to just learn with like zero momentum. Basically you would just be kind of like just searching in the dark a little bit without like thinking back on past experiences, right? In a sense.
If you're not using momentum, then you're only ever responding to the local gradient. And so you're going to take these steps that might not go in the direction that you were going. One thing that we're not considering here, which is going to affect us in actual deep learning problems, is that each batch is going to be a little different. Right? Here we're almost doing batch gradient descent for the whole thing. Once we add stochasticity into the problem and select different samples each set, now we're going to have somewhat unpredictable oscillations here based on how the gradient responds to that set of samples. Whereas if we use momentum, we're likely to be considering contributions from a larger number of samples for each step, and are more likely making constructive steps as a result.
Let's see. Interesting.
So the text then describes a lot of alternatives and more recent ideas. There's a Nesterov accelerated gradient where you're just looking and saying, well, maybe it doesn't make so much sense to measure the gradient from the current point. If I know my momentum is taking me over here, why don't I use that gradient there? That might give me a better answer. This green line calculated from this point is better estimate than the blue line, since we know we're going to move this direction anyway. That's one idea. Some other ones that are presented later are the ADAGRAD, which is an adaptive learning rate method that considers the square of the gradients, and that is going to maybe vary across dimensions, so you're not going to take steps perpendicular to the contour lines necessarily. And if you can scale each one in a reasonable way, you might take a more direct route to the center. So compare the ADAGRAD yellow line to the purple line that you would get without using it. A related method, RMS prop, is improving ADAGRAD by adding some of that exponential decay to the first step. It's almost like ADAGRAD plus, it's the concept of ADAGRAD and momentum built on top of it. Momentum of the squared gradients. And then, of course, we get to one that is more familiar nowadays, ADAM, adaptive moment estimation, which combines all of these concepts and tries to leverage the ideas that worked the best from them. You can see here that it's momentum kind of in the first step, and the second step is taken directly out of RMS prop. The third and fourth steps are little corrections just to make sure that you enable it to learn quickly from the start. T is the iteration number, so this will, for large T, typically just go to M, but it allows a boosted value at the start. And then step 5 is taken from RMS prop directly again. This is a very widely used algorithm nowadays. NADAM is just Nesterov accelerated gradient on top of ADAM. Sometimes that can provide better results, often does. And in the spirit of being exhaustive, the author provides many other thoughts on optimizers as well, including ADAMAX, some second order methods which don't work too well with deep learning given the number of parameters. And TensorFlow has an optimization toolkit if you don't want to design your own methods.
So basically, without optimizers, it actually might not be possible to reach the optimum without the use of some of these optimizers. Sometimes
Either not possible or just impractically slow.
Yeah, I would say that if you understand gradient descent, stochastic gradient descent, it works. In theory, it'll work. You still have the issue of picking a good learning rate, but it'll work. The whole point of these optimizers, and that's why the name is optimizer, is because it makes it faster. It gets it to it gets it to converge to its local optimum faster. In some cases, you actually get a better result. So there's definitely been a whole bunch of papers that show that when you have momentum, you actually get a better local minimum than if you just use vanilla without momentum. But in general, I think the idea is mostly just to converge faster.
I see.
Yeah, thanks, Ted.
All right. No, this is good. And I think it's important to know that there are different optimizers. There's, generally speaking, little harm. If you have a network, you can just change the optimizer and try it with that. You might need to play with changing the learning rate when you switch out the optimizer. But in general, it's fine to just experiment. If you're using a TensorFlow and TensorFlow offers 20 of them, you can pick 6 of them at random, and there's no harm in trying it because it doesn't really fundamentally change things. Not like when you fundamentally change the architecture of your network or something like that. All right, so we're at 1:30, but I think we can go a little over. So if you want to just do the fourth topic, we can try to quickly round out chapter 11.
Yeah, we can summarize it quickly just to. I'm glad we had the chance to discuss a couple of those topics a little deeper. I mean, there's way more in this chapter than you can really fit in an hour. The last bit of the third section, learning rate scheduling, is another great topic. And he goes into a lot of detail in the text here. So encourage you, if you're interested, to look into that. The last section is on avoiding overfitting through regularization. And regularization is just one more technique to avoid overfitting. We've already seen early stopping and batch norm can provide some regularization effects. But what are other ways of doing it? One way is through simple, explicitly writing L1 and L2 regularization into your loss function. So instead of minimizing the data loss, such as the accuracy or the cross entropy or some other metric on your model, you could minimize a function that is a combination of your loss and your model complexity. A frequently used one is L2 regularization, which is otherwise known as weight decay, which looks at your magnitudes, the squared sum of your weights, and penalizes you for having a large squared sum of those weights. L1 regularization is identical to this, except instead of using the squares, you're using absolute value sum instead, which has other properties. He provides some links to regularizers in TF Keras. You see L1 and L2 are options. He shows you how to do it here. He provides a pretty cool interface with partial is a useful function to know if you're designing layers such as this and you don't want to keep writing the arguments over and over again. If you're using a special regularizer, partial allows you to define a partial function of arguments, and then you can just write regularized dense 3 times and it copies these arguments into each one. Pretty useful in certain cases. Dropout is another really important thing to know about if you're dealing in neural networks. What dropout does is it randomly breaks connections in the neural networks. During training with probability P, any given node in some of the hidden layers may just suddenly go away. And he provides a pretty cool analogy regarding employee attendance in an office, right? And poses the question, if a neural network can work with so many of these connections dropped, can an office function if a random number of its employees just don't show up for work one day? And it seems that in a lot of places that's probably going to happen, right? People are going to suddenly take other jobs. Maybe they give their 2 weeks notice, maybe they don't. Employees are going to die. Employees are going to get sick and randomly miss. And if you have a resilient organization, you need to figure out how to handle those situations without losing too much productivity. So interesting analogy. Dropout is typically implemented differently at test time. Once you're running inference, you're going to turn all these guys back on. And then to avoid scaling issues, you want to multiply the activations by the 1 minus the probability to make sure that you're giving your neurons the same magnitudes that they were being given during the training process. Dropout may converge a little bit more slowly, but in some cases the increased performance and improved generalization is worth it. And it's really simple to call it in Keras, just .layers.dropout and give it a rate. One thing that I thought was really cool in this chapter here was the next one, the Monte Carlo dropout, which is a variation on dropout where you're, instead of running it in the traditional way at inference, you are instead actually leaving the broken connections in at inference and doing the dropout and just sampling. So you might sample over a range of 100 different, for each test point in your data set, you might range over 100 different random samples of the neural network and average those predictions together. And it turns out that this kind of works like an ensemble model. You can think of it as an ensemble of weak learners, and in many cases that can do better and give more reliable performance than one single strong learner. So really interesting variation worth looking into.
Sorry, for the Monte Carlo dropout, we actually leave the broken connections in and then sample.
That's correct. Yeah. So there's a
Okay.
trade-off here, right? Because now it's going to take you 100 times longer to do your inference, because for
Right.
each sample point, you're calculating it 100 times with 100 different networks. But in many cases, you can get more reliable results that way,
I see. I see.
according to the paper.
I see.
You can also reason a little bit about the uncertainty too. That's kind of one of the interesting things is if you don't just take the mean, you can take the standard deviation, you can see what's the range of the distribution. So actually, like, we ran dropout a whole bunch of times and we can see like, oh, on this specific sample, we see that there's a lot of variation prediction. So our model isn't that certain about it. And then other ones, regardless of dropout, it still comes to the same conclusion pretty much every time. So that can tell you a little bit about the uncertainty too.
Yeah, and
Okay.
the author gives an example where the traditional dropout gives an extremely high confidence for one class that it predicts, whereas if you run these samples, it all of a sudden it still predicts the same output but with much lower confidence because some of the neural network combinations are lower confidence, and suggests that maybe this is something useful to know if you're in an industry where the variance of your predictions is just as important as the expected value.
Okay. Cool.
Max norm regularization, just another regularization clipping weight sizes. And then the last bit of the chapter is the author's recommended practical guidelines for if you don't know anything about hyperparameters, which ones should I try, and what defaults might work well most of the time. And these are his recommendations for a typical deep neural network and different recommendations for if you're using a self-normalizing neural network, such as a sequential model with the CLU activation. But again, these are not going to work in all cases. Just this is a good place to start. Feel free to tweak it from here.
So Robert, I was looking at this at the end of the chapter and I was saying in the maybe couple years that have elapsed since the book, these are still pretty good recommendations, but I would say that ELU has probably been passed by either Swish or JLU, GELU, slightly different activation functions. And if we want, I can talk a little bit more about those in the next session. I pulled up a couple web pages. And then the learning rate schedule, similar to one cycle, but not necessarily exactly the same. So a lot of people are using learning rates that warm up, where they increase for a certain amount of time. I think this one, he said it's half. So it's not necessarily half, but a shorter, some type of warm up where the learning rates are growing.
I think this one he said Leslie Smith's paper anyway was 1/10, I think was the recommended.
Oh, 1/10. Okay, that sounds much better. I must have misread it. And then once your peak one, it just very gradually decreases over time. And again, the idea is just like with that really cool visualization you showed early on. You want to take bigger steps because you're very far away from the optimum. But once you get closer, you want to start taking smaller steps so you don't overshoot.
I would like to mention something about L1. Technically, L1 means that you drop some of the values, some of the nodes in this particular case. And the thing is with when you use L1, you don't know what is the proportion of the nodes which you drop. There is a promise that it is a nodes which are not very useful. But the thing is that you need to guess correctly what kind of L1 should be to drop exactly the redundant nodes and to keep only the good ones. So in my particular case, I had better experience with explicit dropout. And well, sometimes it was good to take it like 0.3, 0.4, or even 0.5. So he mentioned that it's better to use L2 without any explanations. And from my experience, at least, this is the reason. Then L2 works differently. It works on the reducing the value of coefficients. And L1 just drops out values, and again, just usual dropping out could be more reliable because you're more in control of how many nodes do you drop. Anybody tried it?
Well, if I remember, slightly different comment. If I remember right, the famous Andrew Ng Coursera course, you actually implement L2 regularization. But I don't think I've seen L1 or L2 regularization at all in anything in years.
In maybe not in neural networks. I think
Yeah, right, not
basically
neural networks.
in lasso and other linear models for sure.
Yeah, I think all these other techniques have there's other ways they're dealing with it. And that's really the big surprise, I would say, of deep learning, is that you can have a trillion parameter model and you would think it would just overfit badly. But for whatever reason, the architecture, the training scheme, the regularization, these gigantic models for vision, for NLP, for whatever, they don't overfit badly. They may overfit for certain slight circumstances where you get bad predictions, but in general, it's pretty amazing that something about the way we build them and train them, they don't tend to overfit.
Well, one thing the author recommended where L1 could be an interesting thing to consider is suppose you're training a model and you don't really know how big you want or how big you need it to be, but you know that eventually you want to run inference on it to be lightning fast, and so you want it to be as sparse as you can afford. One thing you could do is put on L1 regularization, which will encourage as many of the parameters in your network to zero out as possible. And then the network that you're left with is much sparser and presumably a lot like the lightest weight version that solves your problem. That's the idea anyway.
Yeah, if you're going to end up running it on
a
if you're going to run it on a tiny edge device, then you need it to be much smaller memory footprint, and you may be better off getting slightly worse performance out of your trained model with L1 regularization than running a sparsifier or quantizer or whatever. That may actually do more damage to your performance if you just do a fully trained 32-bit floating point model.
Mm-hmm.
This is true, but it means that you need to go into your neural network and check out what coefficients were forced to be zero. And then, yes, you can thin it quite significantly.
Yeah, I think it'd be a lot of trial and error. And obviously with L1 regularization, you can still tune the lambda or the whatever the parameter is called, how much you want to penalize. And so that will tune how many of them get zeroed. Cool. Thanks, Robert. You took us through a whole lot of material. That was pretty awesome.
Yeah, it doesn't really do it justice, but it hopefully provides us a starting point. If there's new stuff that you haven't seen, this is a place to look. This chapter has a lot more depth than we could possibly go into in the last hour.
Yeah. But I think this is really good coverage. If you look at like a famous paper, for example, whatever, ResNet 51, whatever. I mean, I think a lot of the things that, they talk about how they trained it and what the architecture is, at least you may not know the very specific details, but I think this gives a good background so that you have the gist of what they're talking about. Yeah. Okay.
Cool.
Thanks. So I think what we're going to do is we have the 2 meetups back to back. And so for the next would have been hour, I'll call it 45 minutes or so. If there's a lot of questions, you know, Ryan and I can stay late. But for the next block of time, we normally have an open office hours, ask me anything thing where we take questions, we talk about projects, different kinds of things. So for those of you who need to go, who are only staying for the book club, thanks for coming. And we're going to transition to that. We can absolutely continue to talk about if people have questions. I have some things I can show just a little more detail. Again, I mean, you could spend way more time talking about these concepts, but I think a couple big ones. But we're also going to open the floor now to things that don't have to do with this particular topic. So I think we'll do the transition now, and so we'll end the recording. And at this point, we'll how we usually do it is we just open up the floor. So if somebody has a project, a question, something they want to talk about, then we just have people, you know, raise their hand, unmute, whatever, and just whoever wants to go.